I'm very, very pleased right now to introduce Amit Sheth as the first keynote speaker for today. Actually, I don't want to say too much about what he has achieved in his life, because that is, from my point of view, absolutely unbelievable. The nice thing about the two of us is that we met, I think, first time at the beginning of the 80s. We both were research assistants at that time, and therefore I was really able to see and observe the development of Amit during all these years, and I really have to say it is, from my point of view, absolutely unbelievable. It's a little bit like his American dream. He was a very, very small guy in the beginning. He became extremely famous in several fields. Right now he is he's with the university, but he is also running a company, so it's the right combination of both approaches. And what I personally like very, very much is I've seen a lot of people who are very, very successful. Some of them are very successful with industry, working at universities, but very successful with industries. Others are very successful with research and publishing researches. Amit is very successful in both areas. This is absolutely amazing. He has published so many high-level papers that is, from my point of view, an unbelievable achievement for his career. So I think we are now more or less done. I'm now very excited to listen to his talk about semantic, cognitive, and perceptual computing, three intertwined strengths of a golden braid of intelligent computing. So it's your turn now, Amit.
I'm waiting for the presenter, the thing to advance the slides. So.
Oh, okay.
Okay.
This microphone, okay.
I don't know how to advance the slide. How do you go to the next slide? It says. Yeah, we are eating into the starting time, and hence the coffee break.
All the time, just use this.
Which is okay. We do the manual approach.
Ours is missing.
Oh, okay, all right. So we are all set. Well, it's I'm going to attempt something hopefully exciting, little forward-looking. There is a term here, golden braid, and some of you might recognize where it comes from. There is a very well-known book, Gödel, Escher, Bach, and Eternal Triangle, and so it's a fantastic book. And in a way, the way work of three different people are brought together from art and music and other things. That is a wonderful, I think, background for that I kind of borrowed from to kind of think about how machine intelligence will develop or might develop, and that's what I'm going to talk about. I thought I will start out with a little humor in that, I'm delighted that I have a chance to be the first speaker in that, and perhaps the maximum audience. Typically, it would have been maximum audience. Perhaps it will be tomorrow, because I know Raj is there today, tomorrow, and nobody would want to miss that talk. I want to remark that I used to look up to Raj and his work even when I was in my formative years of training, and it's fantastic that I'll get a feedback from him once I'm done here. I have a What I will do is to kind of scratch the surface, and I will talk about, so there is this paper that appeared in IEEE Computer last year, which kind of, if you think that I did not make some point good enough, you'll find further details here and some other links that you'll find in the presentation. The presentation is on the slide share if you want to look up in more detail, including the notes and such. The context in which I'm going to talk about is the fact that there is massive growth in data. And a very small amount of data actually that we collect gets processed. And that there is a growth in data of different form, different modality, from text to audiovisual to genomic sequences data to Internet of Things data. We'll soon have 20 billion IoT devices collecting the data all the time, every minute, every second, and so on. What we need to do to intelligently process this data to get actionable information out of it. Data by itself has no value unless it is transformed into smart decisions, unless it is transformed into actions. Let me give you two examples of the challenges that we face. This is an example from enterprise context where there's so many events that occur in the world all the time. How would a cell phone manufacturer like Nokia or Ericsson know that an event has occurred somewhere in the world that could fundamentally change his business unless it acts in a timely manner? So there was a fire at a factory where some of the wafer trays containing important circuitries were wiped out, and basically the supply for cell phone was significantly threatened. Nokia acted in a timely manner and snapped up the alternative supply. Ericsson did not, and that is perhaps a key driver to Ericsson being sold out to Sony, and that's why we had Sony Ericsson after this event. So from amount of information out there, data out there, how do you know what is meaningful in taking a very important business decision? The same kind of thing is also occurring at a personal level. No longer the big data issue is limited to enterprises. For each of us now, we can tap into and benefit from big data. Here, I hope a few of you recognize that. On the left is Larry Smart. He's a fantastic researcher. He's a computer scientist, but also known for his work in quantified self. And he basically used sensors on himself, found out that he has inflammation in his digestive system. And he's a smart guy. He could read medical literature even though he's not a trained doctor. And basically he goes to the doctor and says, I think I have Crohn's disease. How should we treat it? He cannot prescribe himself a medication because he's not a doctor. But the point here is that so much data can be collected about an individual and transformed into very important decision and action plan. Right? And this is, and I'll show you more examples as we go along, this is occurring at individual level as we go on. So whether it is enterprise or individual, there's massive amount of data out there, continuously collected, periodically collected, that has to be interpreted. And that is what the intelligence that I'll talk about. That has to be interpreted to lead to the actions. So in 2004, I used this term called smart data. Now it's very popular in industry also. But the idea is to convert all this big data with these different features of volume, variety, velocity into actionable information and better decision making. Right? And there's more about it if you want to read it. But this is an important slide. And this is where this kind of is my really goal. This is what kind of drives my current and hopefully upcoming research. You see, our human senses are capable of are hit with about 11 million bits per second of information or data. Right now, each of us our senses are able to collect or be exposed to that much of data, right? And you are simultaneously consuming audio, video, text, all forms of data. And your brain does not need separate system. So in computer science, we have great text processing system, great image processing system, great video processing system. And we really need to develop systems where it doesn't matter what modality the data is in, all of them can be consumed in a transparent, synergistic manner. So it is said that our brain is able to convert all that amount of data into just tens of bits per second of what you might call as abstractions that you take away, that you are your cognition is basically capturing that. These are the basic ideas that you're getting from all the sensual information that you're being exposed to, right? So these are the upper level abstractions. These are the things that what exactly am I talking about right now? What is it that you are interpreting? And by the way, you are interpreting that in the context of your own knowledge and biases and experiences that you have. And so it's highly individual also. That in fact all of you are processing the same data that you're being exposed to very differently. And all of you have different piece of those 40, 50, 60 bits of information that you are actually retaining. And for making your decisions, for deciding what to store away and such. So this talk is about, and I would call this as a pedagogy, in that the issues involved in what happens in the brain. I believe it's very complicated to transform that into a computing machinery. So I will be kind of presenting a pedagogy. I'll be simplifying it, presenting it in the form that hopefully we can build sort of componentized system. So I'm thinking of basically the computation in terms of these three computing paradigms that could be very important, and they are synergistic in building future intelligent systems that convert all that data into abstractions that allow us to make decisions and take actions. I also want to note, in just another aspect of my own interest in the continuum of vision that centers around, let's see if this, that centers around machines replacing human, to some wonderful stuff that Mark Weiser and Engelbert and Licklider have said. I'm most interested in this other end, where the computing is there to serve the human, that the human is the master, and that the whole machinery is there to serve the purpose of enriching our lives, which I call computing for human experience. And the idea is borrowed from giants in the computing that have gone before me. One way to achieve this would be to kind of reduce all this into circuitry. And certainly some people are trying this out. I don't have much faith in that. In fact, every now and then we keep on finding out the complexity in the human brain, and the things, the way our brain processes information is quite different, and we learn new and new things about it. So the fact that you can physically say that this thing acts as a neuron and this thing acts as a communication between neurons, that's unlikely to anytime in near future lead to intelligence as I think is necessary. So I take my cue from many different sources, from cognitive scientists, and they talk about this top brain, bottom brain, or left brain, right brain. From neuroscientists, fantastic book by Ramachandran from UCSD, from people in behavioral economics, and of course computer scientists. So there is a lot about it where basically people are trying to figure out how we can emulate the kind of intelligent processing that goes on in human brain. So there's a lot of these things. I run a semester-long seminar to discuss these issues, and I'm going to try to say that in less than an hour today. I'll be using two use cases to make my point. And I would be first to admit that these use cases are not fully worked out, meaning they happen to be work-in processes where I'm able to look at these three components of semantic, cognitive, and perceptual computing. And I'll try to share with you how and what we have done. So let's take this example of healthcare and clinical care. And by and large, clinical care is episodic today. And much for from internal times to now, until very recent time, until last few years, much of it has been under the care of a clinician. All the data that were used to make decisions were created in the under the clinical care. You have lab tests, you have doctor asking you questions, you report to doctor what you are feeling, and so on and so forth. You have other measurements. Your electronic medical records that you can look up. You can look up medical records of what doctor thinks are similar patients, and so on and so forth. That is fundamentally changing, and the healthcare is becoming highly personalized. So you have a lot of sensors, variables that give you information about you, about me, and that there is a lot of information about others out there that is available in a broad sense. Entire PubMed literature is out there available for us to tap into and learn from. But it has all to be done in a highly personalized manner. And I'll talk about personalization in the context of asthma application that I'll shortly talk about. So we have to get individualized solution action plan for anything that happens, and in doing so there will be a lot of data that is specifically created about you, and not just something that is created in doctor's office, and it's created about you under your own control, under the patient's own control. So we have one project, one National Institute of Health funded project called on K-Health for asthma, where we deal with this asthma in children, and there is continuous stream of a whole variety of data that we collect. And we want to, from that, the collected data come up with a better care for individual patient. Things we need to do at a very broad level is to convert that data in the context of variety of knowledge. The knowledge about the medicine, for example, about the particular asthma management protocol that doctors use to manage asthma. And within the context of that knowledge, you need to kind of contextualize and personalize the information, what matters to that particular individual. And then bring up to the abstractions. Abstractions are kind of ones where, oh, this is a wheezing, and level of wheezing is such that you should take inhaled corticosteroid. Or, and that is the action that you would be taking. Or that we have now collected enough data of longer period, and that asthma is not very well controlled, and that you should be taking longer lasting systemic steroid to be able to manage this disease. Right? So this kind of actions is what we want to get to, and the things to keep in mind is that these are the core principles: knowledge, contextualization. Because of all the data, I'm interested in data related to asthma. Of all the data, I'm related to data about this patient. Of all the data, I'm related to coming of something that makes sense to human decision making. So in doing so then, I'm here's the framework of how that data, how contextualization, personalization, abstraction creation happens. It involves semantic computing. As you can see, that allows you to associate meaning to the data and provide a certain level of, I would say, lower level of interoperability among the data. It involves cognitive computing, and you can read the text there, but it's primarily, the way I define it is about understanding and contextualizing the data, making sense that, oh, this, the data represents the fact that your asthma control is not that good, or that this is a, this is considered to be, this is classified as a hypertension. There's a number, but of your systolic or diastolic blood pressure, but that you contextualize to say, this will be hypertension. And then perceptual computing, which would be interpreting and exploring continuously, whereby you are creating, going up the level of abstraction to help you, come up with the action plan. And they are synergistic. There is interplay, and then sometimes the distinction is not as clear cut as I would personally want. But let's see what I can come up with. So, semantic computing can deal with the basic data challenges. It makes data more meaningful, improve interpretability and integration. Cognitive computing can use relevant knowledge to improve information understanding for decision making, and perceptual computing, as I would like to define, can provide personalized and contextualized abstractions over large amount of physical, like Internet of Things, cyber, like web-based, social data, all the data coming on social media, for example, and enable action. And as I look at complex application, not simple, well-defined application like classifying something into this object or object of that type, but you'll see the applications I discuss are very comprehensive and complex. Then you'll see the need for this kind of machinery. So, in case this anything, semantics may not be new to most of you here. Just to be sure, though, it's about associating meaning to the data, or information to say meaning and use of the data. In this context of semantic web, Tim Berners-Lee talked about, it's about labeling the data. So you see here, nice little thing, and say you're labeling. This is the house. This is the door. This is the dog, right? And hopefully, by labeling that, people are interpreting. You can interpret this, convey it to somebody else without even transmitting the image of that. You can be consistent about labeling and make the data more interpretable, more meaningful. And you can deal with the issues such as plate. What is the context in which the plate is used? There are many contexts in which the word plate can be used, right? What happens in a practical sense is that semantics attaches meaning to the observations by providing a definition within a system context or the knowledge that people process. And in a practical level, what happens here is that you have all the observations out there, and you have some ability to represent that in a more richer format. So in the semantic web, we would use RDF, where a relationship are first-class object. Hence, representation level is richer, better than, let's say, relational model. There's a fundamental improvement. And labeling itself is a relationship between what you are describing and what you are describing with respect to. So your concept in an ontology, and you have data here, and when you are labeling that, you are associating the meaning with reference to that ontology. Ontology imply ontological commitment, which imply agreement among the humans who are subscribed to this ontology, right? And that gives you, ability to really understand what the data is, and make it more meaningful. To understand what data is a little better. That level of understanding, as I will describe to you, is still very primitive compared to what we need to get to, but it's very helpful. So in the context of asthma application that we have, and I'll show you, we have a whole variety of data that we collect. The observations come in many different forms. And then I need some form of representation such that I can really reason with it. So sometime in last decade, I had introduced the term called semantic sensor web, and then initiated a World Wide Web Consortium's group on semantic sensor networking. And there, then that group ended up defining, a standard, quote unquote, ad hoc standard that is now widely adopted in annotating sense data. So I use that here for my semantic computing framework. So I have this ontology of concepts: chest tightness, or wheezing, how much activity I'm having in a day. I'm annotating this data with regards to those concepts that are relevant to my context, that of asthma. Ultimately, I want to get to some decisions whether how well controlled is my asthma, right? But this is an important semantic step that we take. Cognition, a little bit more complicated, and there is a lot of work in various fields, but cognitive psychology in particular, and it's about the ability. So you can say it's about ability to understand events, context, and actions, and you want to be able to interpret your environment. You want to contextualize what you just observed, and you want to make better sense of it, whether how meaningful it is at a high level of abstraction. So the example I was that I had given earlier is that it's one thing to have some data about blood pressure. It's another thing to have come up with a feeling that come up with a understanding that this is high blood pressure, level 1. Okay, and that the cognition allows you to have that in the context of all the knowledge that you have in the discipline. So there's a lot more written about it, and I have a limited time. So I'm simply going to talk about it more in a computational context. And I would also be the first to say that I not yet figured out exactly how to transform everything that is said in cognition into cognitive computing per se. But in 2002, DARPA had a project, and they defined cognitive computing as reason, use, represented knowledge, learn from experience, accumulate knowledge, explain itself, accept direction, be aware of its own behavior and capabilities, and so on and so forth. For IBM, it has become a marketing term, and I have, I think, 5 or 6 PhD students who work with IBM research, and I think that there is not necessarily an exact understanding of what it means at a technical level when IBM uses the term, but in a marketing sense it has become rather popular, and you hear about IBM Watson and cognitive computing per se, and they made a distinction between AI and cognitive computing which I don't quite agree with, but be as it may, my take is that cognitive computing uses the way that I would, because I want pedagogy, I want something to be more repeatable. So I would like to build that upon semantic computing, which gives me these annotated observations or even raw observations, and to make them meaningful in context. So, and also it's a system that learns from their experiences and improves when performing repeated tasks. Okay? Just as an aside, there's a lot of interesting discussion about cognitive computing as used by IBM, and there's a wonderful piece by Roger Schank, who wrote a book on that, about how I think there are, in computing we are sometimes making rather a claim that cannot be really supported, and I want to be a little bit careful and not make a very big claim about my ability to do cognitive computing, and yet I would like to show you that there is something happening here that could be called as supporting some level of cognition. The third leg of the stool here is perception. So a ball comes to really your face, and you know that you should duck, and you do that involuntarily. That is attributed to human perception, right? And you have a lot of peripheral vision. Again, that's attributed to human perception. And for me, though, in a more limited context, remember I defined my context in terms of these big data issues, large data issues. So I'm not looking at all the different contexts like object recognition, vision, and such. And others, including Raj in the audience, can say a lot more about that than I can. But this is a cyclic process of exploration and interpretation. Constantly starting at one level of abstraction, trying to achieve next level of abstraction. Okay? So it enables us to focus on the most promising course of action, incorporating background knowledge and provide comprehensive contextual understanding. It also, in the way I formulate it, helps you take explicitly towards taking certain actions and make the right decisions. A couple of slides in how perception is other things, I'm going to bypass them. But there is wonderful reading of John Soa's work and his perception cycle. He talks about this knowledge soup. And in the knowledge soup, basically, all kinds of stuff, all kinds of data, observation, feelings, even fears, and all kinds of stuff that he talks about that may go in there. And there is an observation about the world, and through an inductive process, you look at it, and then you are through abduction derive a theory. And he talks about fragile theory, and and that are constantly through this belief revision, constantly being updated. And through deduction, you could make prediction what might happen. In fact, it might even do better understanding of what's happening, and then help you take an action again that changes the world. And that is how he described this as a perception cycle. What he describes that is rather complicated, and certainly I have not figured out a way to implement exactly as he describes in a computational mechanism. But I'll discuss what we have come up with. So our view of cognitive computing is, perceptual computing is that it asks contextually relevant and personalized questions to explore and interpret observations, builds upon semantic computing and cognitive computing by providing machine to ask next questions or derive a hypothesis. It helps generate abstraction that leads to actions. So that's how I define this machinery. This simple slide is, I think, very useful. At least it has been very useful when I try to convey my thoughts to my own research students. So I have a blood pressure monitor, and it gives me the value 150. 150 by itself is meaningless. There's some level of meaning associated with that. Then you say it is a systolic blood pressure of 150 mmg. So now think you have basically an ontology that has concept related to blood pressure and concept related to systolic blood pressure, diastolic blood pressure, and these units that in which we are measuring. And you're labeling this data. So that is what semantic annotation, and supported by semantic computing. That is good, and I would store that in, for example, RDF as a label, relationships also. The next thing is to use knowledge. National Institute of Health in its Committee 7 has recommended that for typical American, hypertension 1 is defined as level 1 as systolic blood pressure above 140, diastolic above 90, or of those. So fine, good. So now you have knowledge. What is this? Well, this particular thing represents this knowledge, elevated blood pressure. That knowledge by itself is not actionable. Doctor cannot give you medication because the elevated blood pressure could be because of hyperthyroidism, or it could be because of hypertension. And there are different action plans for either of those choices, right? So you need to get to that level of abstraction. So we are going up the level of this chain of abstractions continuously. And in this, developing this kind of solutions is where these three components of semantic cognitive and perceptual computing comes about. Our first attempt to implement perceptual computing was through this what we call as intellego, Greek word to perceive. And how do we make sense of cyber physical social data? And so in intellego there is a comprehensive ontology, and I won't the publications that will discuss that in detail. And what we do here is to translate low level signals into high level knowledge, and large number of observations are converted into hypotheses. And then, that could explain what you observed. And then you are, looking for discriminants to then further refine and choose among the valid hypotheses that you have. Right? So there is another paper, and that paper appears in the proceedings of this Web Intelligence, where I specifically talk about the role of knowledge and I discuss 4 very specific applications. A couple of them are new applications of the kind that have not been solved before, at least to my knowledge, and distinctly isolate the role of knowledge. My purpose was to say that, to recognize that there has been immense success of machine learning, and to some extent the role of knowledge has not been adequately understood and exploited. I had a semantic web company I founded in 1999, and we developed the first commercial semantic search engine in year 2000. But that's a small company, and it had a niche. It had a broad product, but then because of the internet bubble burst, we went to niche market in financial market. So when Google in 2013 came up with semantic search and they had knowledge graph, people started seeing the value of knowledge graph. And I just want to say the following thing to make an important point, that Google used to do very good semantics, very good search, right? It was still a dominant search engine before 2013. But now you can recognize how important the knowledge graph has become to everything that Google does. Google also has a healthcare knowledge graph. So when you give a query that may be related to health or clinical issues, it will use that knowledge graph to interpret that query that you gave, so search term you gave. So and there is a semantic web did not progress too fast enough in my view, and there were quite reasons for that. I don't have time to talk about that. But I think that role of knowledge is you're going to see much role of knowledge in conjunction with machine learning and NLP as we go forward. Coming back to our example, you could have knowledge represent the simplest form, maybe this form here of a simple graph, and then what we do here is to do this abduction and deduction, so we can have explanation and we can have description. Now this machinery is discussed in detail elsewhere. I won't go into that. So for example, you have observed symptom of palpitation, and it can be explained by hypertension or hypothyroidism. And then you seek out additional observation, and if you find the appropriate observation with regard to climate skin, then you can distinguish between these two explanatory features and say, oh, okay, in this case, based on the climate skin, I see this hypothyroidism. Okay? And so in that context, we worked on this augmented personalized healthcare application. The idea, the application is about, we apply that to asthma. We also have, the same thing being done in dementia, and we are applying the same thing also, same general framework to obesity kind of thing, and asthma obesity nexus. I have a video here. I won't play, but the video shows tool that the kit that we have built, a mobile app we have built that talks to, that constantly collects data from sensors that using Bluetooth, and also collects the data from web services about a variety of other things, and some applications and so forth. So in our system, for example, we collect broad variety of data: personal schedule, sleep data, activity data, personal health records, community data. From all that, we want to be able to really help manage an individual child's health issue, in this case asthma. So there is this application, I won't, and a mobile app, and it just shows some snapshot of question answer that goes on. There are many mobile apps today out there. By and large, these mobile apps have very limited utility. And we have dashboard that help you visualize the data and so on and so forth. Again, this is overwhelming, both to the patient and clinician. There's just too much data, even that. No doctor has time to look up all the data that is generated, that is collected in by patient 24/7. The system has embedded knowledge. It uses the knowledge. So for example, if you have mild persistent asthma and is not well controlled, you would be prescribing medium inhaled corticosteroid. And that our role is to be able to kind of help understand whether it is a mild persistent asthma, whether it is not well controlled, and help patient basically provide the action plan to follow the regimen the doctor has prescribed. Because of the FDA regulation and all that, we can't be giving clinical advice, so there are caveats that I won't talk about here. What we look at is that with all that kind of data and all this internal framework of semantic cognitive perceptual computing, what we want is this kind of thing. We want to be able to tell the patient, take medication before going to work, contact your doctor, avoid going in the evening due to high pollen levels. These are the kind of stuff that are important, that are actionable, that we want from all that data that we generate. So the data we generate is massive, right? We have, for example, indoor air quality monitor that gives you carbon monoxide level, that gives you particulate matter, that gives you humidity, temperature. We have outside pollen count, we have outside smog levels, smoke levels. We have Twitter data on people talking about asthma in the local area. We have public health related signal. All of that has been collected. And from that, you need to come up with some very simple thing, diagnostic. How well controlled is your asthma? So you want to be able to say in some color-coded or some simplistic manner exactly how well controlled your asthma is. And then another very important question, how vulnerable you are to the asthma. So for example, is there something happening around you? Has anything changed that could increase the probability that you would have asthma attack, so that you can take preventative action? That is the kind of thing that you would want to come about. So in this case, you can see, from the data, of broad variety of data that you are collecting, like what is the air quality indoor and what is the wheezing level and all that stuff. You're trying to come up with something saying, close the door, windows at home during the day to avoid carbon dioxide inflows that increases the chance of asthma at night, kind of stuff. There's another example of a richer model. One of the things that always bug me is that in the computer science, and at least in my early years when I was doing my coursework, we would be working pretty hard about limited memory and space and time trade-off and all that kind of stuff. But a lot of computing in 80s, most of the 90s, really focused on how do you reduce a rather complex real-world problem into a computational representation that is minimalistic, or that's just enough or sufficient. Do the computation and then interpret that computation, more or less extrapolate. So you formalize, but you give up and a lot because you wanted to use limited richness in computational models. So for example, one of the reasons I feel that semantic web did not succeed in earlier days was rather too heavy reliance on description logic. They say, oh, that is computationally tractable and that kind of stuff. But really, if you can't capture the richness of real world problem, what value there is to solve a problem that is not captured in the right level of richness. So I always look for capturing expressiveness, even though that creates challenging computational issues. But lately we have been doing a lot more progress. So for example, we'll increasingly use probabilistic graph models, and that really captures the richness of the knowledge in more detail than what you will capture in a logic-based framework. In the context of a lot of information that you could get about, let's say, traffic. What we can do now in solving traffic problem is that we can actually collect broad variety of physical cybersocial data, and then help answer the questions. This is just a slide in passing that we have, more than billion cars, and we are going towards 2 billion cars, and there's a lot of traffic jams and so on and so forth, but we need to be able to ask the broader questions. What does it mean to me in my commute, as an example? Or the city managers need to ask questions related to traffic in different ways. Today there's so many sources of data that reflect traffic. So you have road sensor data, your sensor data, data created by mobile applications, your data on social media. Now the problem is challenging. There's a lot of non-linearity in traffic data. So you would have, for example, an accident and you have slow traffic. But the challenge is that different accident at different times would create different impact. So it's not something very simple. You have different events. Each of the events, again, what time the event is, what are the nearby roadways and traffic conditions there, is a weekday or weekend. All of them would have different, choices. So here we, after going through looking at some various choices for representational models, we settle on linear dynamical systems as a more comprehensive representation of data analysis that we would do. And we took the data from 2,534 links. These are basically road links from San Francisco Bay Area. And for 24 hours a day and 7 days a week, that means 168 times, that we had to learn the models for each of these links. So each of the links, 168 models had to be learned, right, to see what is normal traffic pattern. Because we only need to we really care about what is abnormal traffic, right? And from that, we figure out a way to tag, identify anomalous data and tag anomalous, what is anomaly, right? And thus come to kind of understand that the various situations, anomalous tagging will be, this was an accident related slowdown, this was a road resurfacing related slowdown, this was a sports event related slowdown. All that was to be learned. So there's a lot of computation that goes on. A lot of data is pre-processed to understand the situation, the world, real world as it is, and then to come up with understanding of what might be happening right now and interpret what might be happening right now. Why there is a when you observe that there is a traffic slowdown, how do I interpret that traffic slowdown in the context of all the knowledge about the real world that we have generated? And so we may come up with a variety of explanations when the things deviates from the normalcy of the operations and what should be expected at a particular point of time. Complementing this, and very interestingly here, is the role of social media and social data. So we had another project, we are part of one of the EU Framework 7 project called City Pulse, and work with city of Brasso and Aarhus. And we wanted to ask, are there really high quality social media data that are relevant to various city departments? So you can see here these are different city departments: healthcare department, education department, transportation, environmental department, and so on and so forth. And we basically demonstrated ability to isolate the tweets or social media content posts that are quite relevant, among all the noise that you would have on the social media. Now, what made this thing click further, and how we could build this, semantic, cognitive, and perceptual computing based computational environment. So, in this particular case, knowledge played very important role. And I want to make another interesting point here in the passing, in that when we want to solve real world problems, we can't be really very purist. So in our case, for example, we wanted to use all the available knowledge for that is relevant to that. So we use OpenStreetMap for locations. 511.org has a hierarchy developed by domain expert related to transportation. And then Scribe ontology is developed by IBM with respect to smart city related operations. And all of them use different representation. One of them is in OWL, other is a taxonomy, and other is more of an RDF, RDFS kind of representation. You need to be able to deal with all of the heterogeneity. Because the knowledge is not going to come from one person modeling everything in a one particular representational framework. In this context, let me show you just one simple point. So this is a tweet here. You can see the tweet here. Last night in California, Half Moon Bay Brewing Company with others, something like that. Understanding this tweet would be very hard. Entity extraction, relationship extraction, emotion, sentiment, intention, severity, many things can be understood from this kind of content. These are challenging problem. Just with respect to the entity extraction, having 5-gram extraction is not an easy problem, right? Half Moon, so Half Moon is a entity, Moon is an entity, Half Moon Bay is an entity, Brewing Company is an entity, Half Moon Bay Brewing Company is an entity. And it is use of knowledge base like this that make this possible. Yes, you can use CRF, and we did use CRF. And the CRF is well tuned for really find the chain kind of related content. But it was the combining CRF with the use of background knowledge that made this possible. And in the context of processing, then we could find out when you get information from, you can see on this side, information from road network and information Twitter. You find complementary information, you find corroborative information, you find timely information, you start seeing fog-related information from this kind of data, and then you start talking, tweets about slowdown of traffic due to fog from the social media data, right? Let me show you one other interesting thing that happens here internally, and that is you see there is a traffic slowdown here, and the explanation for that was aided by this tweet here where it talks about an event on the Golden Highway at the Viking blah blah, and talks about a truck, and that from that we need to map that into overturn truck as a described concept in the knowledge base, in the knowledge model, and develop the understanding and explanation, and saying, oh, okay, so overturn truck on this traffic in this kind of day, what is the typical traffic resolution pattern? And how can we make sense of all these things? So you can see that a lot of these things are possible because of these are rather complicated issues, challenges, because the road understanding of road related events is not easy itself. You have many types of knowledge, as I described. You have many form of multimodal data that I described. You have to use spatio-temporal reasoning. Within that, you have to do further contextualization of transportation data. Within that, you have to do personalization of your traffic, route, and see what is happening in your traffic route of interest to you. Within that, you try to understand, interpret the event, what that event means to you, and whether you should take this route and wait for the traffic, go through this traffic, or you take alternate route, and then make your action plan accordingly. So this example demonstrates use of multimodal data stream, multiple sources of knowledge and ontologies, semantic annotation, rich representation, in this case probabilistic graph model, statistical approaches to create normalcy models and understanding of anomaly using historical data, explain anomalies using extractive events, providing extendable information. All of these are involved in making sense of this kind of stuff. I know Rainer is getting a little ready to push me out here. Let me put together all of the things that I said in kind of one slide. So what you see here is, this you can again read about it in a lot more detail, or we can talk offline in that paper that I talked about. But here you see this example more of healthcare, and we have health data, all the physiological, environmental observations, all the health signal abstractions, low activity, high pollen, and then health condition insights and treatments that are there. In this other example, you have data of different kind and ontologies and models. Both ontologies and models, remember, that are important, coming from many different sources. Look, extensive data processing to come up with the models in linear dynamical system. Declarative knowledge guided piecewise linear approximation of normalcy and abnormality detection, and then predicting traffic flow in a city, explaining sensor data, time series and anomaly, and so on and so forth. Underlying machinery could utilize semantic computing, cognitive computing, interpretation with regards to all the knowledge you are able, and constantly going through this cyclic process of going up the level of abstractions to come up with abstractions for decision making, prediction, actions. So as I said earlier, these systems interact very thing. But pedagogically, this allows me to kind of create a framework for solving rather complicated, challenging problems like here with diverse data, diverse knowledge, a lot of possibilities in terms of understanding and explanation, and important implications of the actions that you can take in developing these kind of solutions. So these are my colleagues and the students help, and my group. Just wanted to acknowledge them.
Yeah, thank you very much. I think we should take time for a few questions.
So my question, so if we start, let's say, from raw data, we go up, we have personalization, and next we have, let's say, at the very end, making prediction and actions. Now, obviously, if I drop personalization, then the actions which we'll be taking, most probably they will be wrong. So this is why we need personalization. Now, the better is the personalization, then we have more chance that the action which we'll make will be correct one. So let's like in the medical area that will not prescribe, let's like, wrong treatment. But the problem here is that if the personalization is getting too precise, then the coverage goes down. It means we will not cover, let's say, all new patients showing up. So can you comment here? It means how to, let's say, look at for some kind of a threshold between personalization and general system, not to lose this coverage.
Excellent question. I should mention, though, that this is not an abstract problem that we are solving. Right now, as we speak, we are undergoing a pilot or kind of a, what you call mini-scale clinical trial with 200 actual patients. So I work with the real doctors and their patients, and this is a real kit that is collecting real data, and we are trying to validate this machinery and of course develop the solution. The question is that there can be trade-off or possible challenge between just personalizing your information and not paying attention to the new things that you can learn from, let's say, large cohort of people or other, let's say, the scientific literature, for example, or new studies that come up. No, that doesn't happen here because so as at least in this particular framework, what happens here is that the cognitive computing component, quote unquote, is one where it is looking at contextualizing understanding of the data. And the context here is not necessarily just that particular patient, but the context is all the available data. And hence, if I'm collecting data for the new, from the new patients, and then I'm interpreting it as the time goes along. And so even in the SOAS cycle and other cycle, other thing of cognition, you always learn from the other things that are happening surrounding you. So in our own approach and the next generation of system we are building, we are also analyzing so we have access to PubMed, but we are also analyzing the electric medical record or clinical notes of all the patient cohorts in that study. So, so the analysis is not limited to simply collect data collected for this individual patient, but the entire cohort that is happening, that is in the study. And then interpretations are done with respect to the entire cohort. But paying attention, so one very important, we have, let's say, a sibling, both of them have asthma, but one is more sensitive to ragweed pollen and other is less sensitive. Exposed to the same condition, one gets the symptoms related to that could lead to asthma, other does not. And the thresholds for both of them are, for getting symptoms are different. So observing that is very important. While the general thing about the fact that data, our solution, for example, are very appropriate to Dayton area only, because some of the data we use in terms of pollen in the ragweed season is August, and tree weed season is spring, and so but the level of ragweed in Dayton area is very different than the level of ragweed in Utah somewhere or Nevada somewhere, and hence that contextualization is also very important and is certainly taken into account in addition to the personalization.
Yeah, thank you very much. I think we have to postpone any further questions for the break, so Amit will still be available. I'm pretty sure that there are many more questions. It was a very, very exciting, or it is a very, very exciting topic. And okay, one quick question. Okay, we cannot refuse it.
Dr. Sheth, excellent talk. I'm trying to understand your bracketing. Are you saying abstractions and prediction and action is not part of cognitive computing? If you look at the
you see, there's a slide that I had much earlier where in the cognition cycle the prediction is also there, right?
I was trying to understand your definition of perceptual computing, semantic computing, and cognitive computing. I was looking at your bracketing.
Yes.
And I'm saying it looks like the way you have bracketed them, abstraction, prediction, action, is not part of cognitive computing. If you do say that, IBM might disagree with you, right?
I have no problem disagreeing with IBM, but I would say that. Let me so give the context. So I think Rajesh asked a very important question as to how do you really kind of componentize this, and that's why I made important point earlier on in my talk that this I realized there is level of pedagogy here. I want to somewhat simplify the things such that I can convey the things. The real world is messy, very messy, and I try to hopefully cover that with the examples that I took. Here what we did is that, you see, the semantic computing is relatively easier part here, right? In the cognitive computing, what we are trying to do here is that we have historical data. I talked about electronic medical record data. I talked about PubMed data. We have the knowledge bases and asthma related stuff, and we are contextualizing data and what it means. We have looking at the data related to Dayton and all that. That is all coming up in the cognitive computing part of what I'm saying here in this particular way of componentizing the challenging. In the perceptual computing, I'm always trying to go up the level, and I'm doing that cyclic process. I showed you in the intelligible process, the explanation and the the action plan kind of thing, right? You get creating abduction, deductive cycle. So you are always trying to interpret the new data comes up, and then you are trying to go from in that pyramid I show. When I'm explicitly trying to go from the lower level of abstraction to higher level, taking the steps consciously to reach the level at which I can make decision, where I can get to hyperthyroidism or hypertension. That process I am calling perceptual computing in my thing. right? So all that contextualization I'm putting in cognitive computing, all of that computation that takes me up the abstraction level, I'm calling it perceptual computing. That makes it pedagogically is a good story for me, and gives certain level of clarity. Otherwise, if you look at the literature, and I showed the book, and I'm sure you looked at all that in cognitive psychology, all that, there's a lot of jumbling of the stuff. And SOA cycle, if you read that, it's pretty complicated thing, and a lot of converting that into something that is that can be implemented. And at the end of the day, I'm really an experimental scientist, not really a theoretician. And so for me, it has to be converted into systems. To develop a system, I had to have that clarity, and that's how I got here.
Okay, thank you very much again. So we will have a break now, and we will continue with the next keynote at 11:30. Thank you very much again.